Good afternoon, folks. So let's get started. Hope everyone's enjoying the snow out there. So just a couple of announcements. We have our first midterm next week, next Thursday. So according to the syllabus, it's next Thursday in the evening. I believe there's a bio exam or math exam. Bio exam the same time. So we've instructed you to fill out the makeup midterm if you have a conflict such as a class or another exam. All right, so that page is actually posted now. I was linking to a dead page for a while. I'm sorry about that, but it now is posted. So if you have a conflict, please fill that out. It's on the home page of our Carmen site. It says midterm makeup policy request form or final. Obviously click on the midterm. All right, so recall that we finished chapter 1 last week, right? And I want us to get used to the pacing of this course and understand what homework, the online homework, what that is used for within this class. So I just have some tips here for our homework sets, because that was due for chapter 1 was due on Sunday at midnight. I think the majority of you completed it. So I'd like to remind you of the grading policy. Incorrect responses are penalized. So it does, make the most sense to get the question right on your first time. This term I have introduced a grace late policy for homework. So we're currently in our 2-day grace period. All right, so over 48 hours, you can continue to do, questions you skipped, or if you just completely forgot about the homework, you can continue to do it for a linear penalty. But then after that 2 days is over, basically the, maximum you can earn is 10% of the original 100% of the homework. And this is just to incentivize students to revisit old problems that they didn't get to. So, I like graphs. So it kind of looks like this, right? That, where's my pen? Right, up until the due date, obviously, the due date, the Sunday at midnight, isn't a due date like D-O, like D-U-E and D-O, it's due. It's not a due date. You can do your online homework before that due date as we're working on it in class. But then once that due date on Sunday comes up, then there's that penalty, and then 10% until the end of the year. And so you can revisit those questions. I have some data I want to show. All right, because I think it's really powerful. I want us to think about what is the value out of these homework assignments. Think about, how do you approach this online homework? Do you just brute force your way through it to get through it as quickly as possible? I'm gonna ask you to think about homework a little bit differently. Are you trying these questions on your own for the first time? I don't want you to be trying these homework assignments, questions like this, for the first time. I really want you to think about homework as a tool to demonstrate your knowledge, all right, within the skills and concepts that we learned in class. So this is the data that I want to show you, all right? So this is the scores, the online homework scores from the last term I taught. So this is 400 data points. So I ordered these graphs based upon their online homework grade. So the one in the top right, these are the students who earn 95% of the online homework grade total. And then those are the distributions of the grades that they got. All right, so that's 95% or higher. The next grouping I have is 90 to 95%. So you see that the frequency of A's definitely decrease and kind of goes more towards the B+ range. You see that? Okay, and then we go even lower, like 80% to 90%. I mean, in my idea, that doesn't seem like a really bad homework score. I think that's a pretty average homework score, you think, but you see how the distribution of grades goes even further, where the highest frequency is a C+. And then finally, this is the best way I could show this data, but online homework students who earned less than 80%, see how that frequency shifts even further to a C range, but then we see a bunch of E's or failing grades show up. And I don't mean to show this to you to scare you or anything, but really, if you think about homework as a tool to demonstrate your mastery in these chemistry skills, it'll take you a lot further. Don't just brute force your way through it. Really learn these concepts before you answer those questions. If it's just a check mark of a thing you have to do on Sunday night, you're not getting the most out of it. All right, so I'll post these slides eventually, and I'll note that the average online homework score from my last semester was an 86%. Oh, and I'll also note, most of these E's, like 2/3 of them, the students earned less than a 65% in online homework, all right? So take that into account. You know, you might be thinking back there like, oh, online homework it's only 7.5% of my grade, but it makes a difference, all right? So how you approach homework will really set the tone of the grade that you may earn at the end of the term. Do we like that graph? Do we like this graph? Okay. All right, I like data. Okay, I'll post this on our page somewhere. Okay, so where do we leave off? Okay, we were just at the end of talking about isotopes, right? And we were thinking about isotopes and how isotopes occur at different percentages, different natural abundances for substances. So we looked at lithium. Lithium has 2 different natural isotopes with different abundances. And so how we calculate the atomic mass that comes off the periodic table, this is a weighted average of the isotopic masses of them. So you think, you know, when you take an average of something, you just add up the 2 numbers and divide by 2. Well, a normal average that you and I are thinking of, we're making the assumption that all of the numbers are weighted equally. But within isotopes and natural abundances, they don't occur in equal abundances. So we have to take into account the percentages that they occur. And like we said, with this lithium case, we know that lithium, its atomic mass is close to 7, it's 6.9, and I asked you guys which isotope occurs, you know, in a bigger proportion, and everyone said 7, you know, instantly, because we see that average is closer to the 7 number. So if we actually drew a mass spec of what a lithium sample would look like, it would look like something with a little blip at 6 AMU, right, and then a bigger blip at 7 AMU, and that would be what and then this would be signal, and this would be AMU. This is what a mass spec of a natural lithium sample would be, and what we're basically saying is that 7.5% of the signal is coming from 6 AMU, and the other 92% is coming from that 7 AMU, and that's how we get that average, that weighted average that's close to 7. So this is one way we can use that weighted average equation, all right? There's another one that it's essentially the same kind of question. We just ask for a different bit of information from that weighted average equation. So here, same type of thing. We have 2 different isotopes. I give you the isotopic masses. But here, I'm asking you what is the natural abundance for each isotope. So the way we approach this question, hopefully you did it at home or started it, make the assumption, so just say that one of the abundances of one of the isotopes is X. So if that one is X, that means everything that's left over from 100% is the other isotope. So we say that it's 1 minus X, where X is, I'll just define it. This is your fractional percentage, right? And then we just set up our weighted average equation exactly the same. So the value, the atomic mass off the periodic table, 10.811 AMU, that is the weighted average. All those masses that you see up there, those are the weighted averages. I give you the isotopic masses, so just associate the correct abundance for each of them. So this first one is boron 10. The second one is boron 11. And so now it's just a bit of algebra. Okay, so how I do this is, you know, I multiply these 2 together. So this is 10.013x plus, now I need to distribute this. All right, so it's plus 11.009 minus 11.009x, right? Oh, and I forgot the other side of the equal sign. So this is 10.811. So now I just kind of group everything together, group the x term variables together, and then the coefficient terms together. So what I will do probably is subtract 11.009 from both sides. 009, so I get negative 0.198 equals, and then add those two x terms up. So it's negative 0.996x. All right, and so since there's a negative sign on both sides, they just, you can just cancel it, make it positive. I don't know what the right math term is for that, but just make it positive. And so then divide both sides by 0.996, 996. And so we get that x is equal to 0.1987. Okay. So there's our answer, but as chemists, we need to make sure that we can associate that number with its meaning, with its significance. So what is the significance of that number, 0.1987? What did we just calculate? So x is what? What did we define x as? That's what we need to look at, yeah. Yes, the natural abundance, and specifically of which isotope? Boron 10, yes. So we got to look back at what we, assign that variable to. This is the natural abundance. Well, it's the fractional natural abundance. So it's really 19.87% is the abundance of boron 10, because that is what we assigned it as. And then we can calculate the abundance of the other one, right, where we just do 1 minus that number or 100 minus that number, and then it is something 80.13%. Okay, this should actually have 3 sig figs. I'm sorry. There we go. So it should be 19.9%, and then it should be 80.1%. Should be our answers for boron 11 and for boron 10. All right, so make sure that you can do questions like this. It's the exact same as the one we did previously. We just assign a different variable this time. Within the overview sheet, I have a lot of different examples of essentially this same equation just asked different ways. All right, so let's do one more. This is straight from an exam. Yes. So in nature, magnesium consists of 3 isotopes. We have a sample of magnesium. We send it through a mass spec. Which mass spectrum is this sample of magnesium? So there's a lot to work with here, okay? So we are looking at mass specs of magnesium. So we need to recognize that a sample of magnesium, when we throw it into the machine, into the instrument, we are looking at millions, billions, trillions of magnesium atoms. So we're not looking at one single isotope, we're looking at the whole natural abundances of all of the magnesium isotopes that there are. Right? That's why we see 3 peaks here. So I guess there's 3 different isotopes of magnesium. So recognize here that these peaks we see are the natural abundances of all of those isotopes. They represent that. So what this question doesn't give us, though, is the weighted average of magnesium, unfortunately. But is that a problem? No, because where can we get it? It's on the periodic table. So the weighted average of a natural occurring magnesium sample, what is that number? Actually, I have my periodic table here. It's 24.31 AMU. That is what we say the atomic mass, or we can say it's the weighted average. So we want to see which one of these graphs represent a weighted average of 24.31. So why don't you take a minute, discuss that with someone near you, and we will come back to it. So I hope we got to this point that, recognize magnesium has an atomic mass. We need to pick the graph that has that weighted average. So which one do we think it is? You shouldn't have to do any calculations. You should be able to see where that average should lie based upon how big those signal things are. Yeah.
I know for this one, since you're not doing calculations, it doesn't matter, but usually if you're taking a number from the other table, should you round it off?
You should never round off a value that you can easily look up.
Okay.
Why is that number? Oh, that one. Okay, yeah, because I was looking at a different periodic table, so yeah. Yeah, it depends on what you get. All right, so let's just go through them one by one and kind of estimate where that weighted average is. So I'm going to work through it backwards. Okay, so number 4, the weighted average, how I go about it, I don't know how you go about it, but I see, okay, there's 3 peaks. The 24 and the 26 will like cancel each other out, so the weighted average is going to be 25. Did we get that? So is 4 the right answer? Probably not. Hopefully we can get something closer to 24 point whatever. All right, so this one, we have, again, 3 peaks. So I see this peak and this peak are equal sizes and they cancel each other out, right? That's what I see. So that means the weighted average will be wherever this is because it's halfway through, like halfway between. So I don't know, what is that about? Like 24.5-ish? Yeah, okay. All right, so that's closer, but not quite. So let's go to this one, number 2. Same thing. So what do we think the weighted average is? 25, because these 2 peaks kind of cancel each other out, and the middle, like the middle of the data is 25, so it's not that one. All right, but this one. So how I think of this one is that this peak, this signal 24, your answer is going to be really close to 24. But then those, 2 little peaks that are higher are just going to shift the average a little bit. So I think the average will be, just like a smidge higher than 24. All right, so I think 1 is the correct answer. It's going to be the closest to 24 point, what is it, 3? Yeah, 3 AMU. Another reason why 3 is not correct, all right, so 3, we said is 25.5, but typically mass numbers don't occur in half increments. All the AMUs that we've been seeing have been pretty close to whole numbers, okay? Did we get that? Okay, all right. This department likes conceptual questions where you don't actually have to put in numbers, but you have to think about it. You have to know how the numbers work out in order to get questions like this. Okay, so let's keep going. So there's all that stuff. So now the rest of the chapter is being able to use the periodic table and name different substances. So if you don't have your own periodic table, definitely have one handy all the time for your studies and homework. It'll just be easier for you. All right, so the periodic table. You will always be given a periodic table on exams. All right, it's not going to be a fully complete one, but you'll have all the information you need from it. So here is our periodic table. It is ordered in this way for a very specific reason, and we'll kind of expand on it more in later chapters. But the parts of the periodic tables that you should know right now, being able to differentiate between a group and a period. A period is a row, so this is a period. So I can say that like sodium and magnesium are in the same period because they're in the same row. Or sodium and aluminum are in the same period because they're in the same row. Right? Group is a column. So oftentimes I'll say something like group 2A elements. So you look at group 2, they're all numbered, and I'm talking about all the elements in group 2A, so like beryllium, magnesium, calcium, things like that. So those are all the elements in a column, right? So make sure you have that differentiation there. Group elements, or a main group element. So oftentimes we talk about main group elements. These are essentially these 2 blocks of elements. So these in the middle here, these are our transition metals. Or elements. So that takes care of those 2. And then lastly here we talk about metals versus nonmetals and metalloids. So I'm just going to erase these things that I just drew. So how I identify where metals versus nonmetals are is I locate this stair-step looking thing on the right side of the periodic table, and I recognize that the elements along this staircase, these are my metalloids, or semi-metals, metalloids. And on the right side, we have nonmetals. So over here, we have nonmetals, And then on the left side, these are our metals. So we see that it's not like two distinct groups, metals versus nonmetals. It's this very gradual like shift from one characteristic to another. And that's why metalloids kind of occur in the intersection, or where metals and nonmetals meet. So that's where our metalloids live. All right, but in general, what I think is, okay, metals are on the left side of the periodic table, nonmetals are on the upper right-hand side of the periodic table. So the last thing here is that hydrogen is special. Hydrogen is special, and that's related to this question that I posed right here. If you're looking at this periodic table, you might have noticed, why does hydrogen show up twice on this periodic table? That's kind of weird, all right? But it's because hydrogen is special, because based upon where it is, we would categorize it as what, a metal or a nonmetal? A metal, because it's on the left side, but it's not. Hydrogen is not a metal, it's actually a nonmetal, and that's why this particular periodic table, it shows up on the other side with the other nonmetals, because it behaves more like a nonmetal. All right, okay, and then so oftentimes we use these common group names. All right, so 1A, 2, 7, and 8, those correspond to different columns, and there are the different names for those. So I might refer to, group 2A elements as alkali earth metals, and you should know right off the bat that I mean a group 2A element. So there we go. And we use these terms very, very often, or halogens is group 7A elements, so right here, not hydrogen. So it's weird that is there. And then all periodic tables you see should not have hydrogen over there. So you just need to know that hydrogen is special and it's a nonmetal. And then group A, 8A are noble gases. So let's practice using the periodic table. So let's name a halogen in period 5. So halogen means what group? Or what column? 7A. So this is like battleship, right? So we go to group 7A, so here, and then we count period 5. So 1, 2, 3, 4, 5. So here it is iodine. So iodine. All right, alkali metal in period 3. So alkali metal means what group? Go back one slide. 1A. So that alkali metal in period 3, so that would be sodium. Na, sodium. Okay, you can do the other ones. Let's do this one. Name 2 group 5A metalloids. Okay, so I already tell you the group, so we look at group 5A, so right here. All right, so which one of these elements in this column, sodium to bismuth, would be a metalloid? Oops, I pointed at it. It would be the things that are on the stair step. So the 2 metalloids would be AS and SB. So arsenic and antimony. SB is antimony. There's like no common letters in that name, that specific name. All right, so what is it? I said it's arsenic and antimony. Name a group 4A nonmetal. Which one? Carbon. Are there any other nonmetals in group 4A? No, there are not. Yes, so carbon is the only nonmetal there. Very good. So that's how you use the periodic table. Okay, so let's keep going. So how else can we use the periodic table? It will help us predict the charges of ions when we get to there. All right, so an ion. Up until now, we only talked about pretty much neutral atoms, where protons equals the number of number of protons equal the number of electrons. An ion is just where protons and electrons are unequal. We have 2 different flavors of ions, either positively charged, that's a cation, or negatively charged, that's an anion. How I memorize that is that cation, a T looks like a plus sign. And I literally still use that today. When I want to know which ion, if I want to be specific, I have to remember that cation, the T means plus. Anion just means negative. I have nothing to memorize that one. Okay. All right. So an ion basically has an overall charge where it can be positive or negative. So where we can calculate the charge, it's the same equation we used for our atomic symbols. Charge equals number of protons minus number of electrons. Okay, so specifically we can talk about anions, where a neutral atom gains an electron, or either one electron or multiple electrons. How we typically predict anion charges from the periodic table. Let's see, charge of an anion is equal to its group number minus 8. That's how we predict non-metals becoming anions. And I'll actually make that distinction. For anions, typically non-metals will form anions. Okay, so if non-metals form anions, then that means cations are typically formed from metals. So for metals, we make a cation. If we start with a neutral metal atom, they lose an electron, and that's what you see in that equation there. It loses an electron, so the product is overall plus charge. And so we can predict the charge of a cation. So I'll differentiate this. Charge plus is typically equal to its group number, most of the time. So for example, if we look at the periodic table, calcium is in what group? Group number? Calcium's in what group number? 2. Is it a metal or a non-metal? It's a metal. So metals typically form what type of ion? A cation, so positive. So that means calcium will probably, if it's an ion, will be a calcium 2+ cation. Or if we look at fluorine, fluorine is in group 7. 7A, it's a non-metal, so it'll form an anion. So the charge, if fluorine will become an anion, will typically be F minus 1, because fluorine's in group 7, so it's 7 minus 8 equals -1. Yeah. Or you can think about it, we'll get to it in later chapters when we actually talk in more detail about electrons. It's how many electrons to get to a noble gas configuration. All right, if you've taken chemistry before, it's the same type of thing. All right, these next 2 slides, you essentially just need to memorize these. Okay, and I don't mean before the midterm, I mean like before Wednesday, you need to memorize them. Because if I am talking about a substance like calcium nitrate, I want you to be able to know in your head what calcium nitrate looks like. All right, so these are some common cations. A lot of these, you can just predict the charges of a lot of these, like with the equation that I just said. So here you can see a lot of the +1 charge substances are group 1A substances. These 2+ cations, a lot of them are 2A substances. The cation that you need to memorize is this one I have highlighted, NH4+. This is the one polyatomic cation that you need to memorize. So what do I mean by polyatomic? All of the other substances are just monoatomic, meaning that there's just one atom, one ion particle there. But NH4, there are actually like 5 atoms just all together with an overall positive charge. And so that substance is called ammonium. And that's the one polyatomic cation you need to know. Within anions, there's a lot more polyatomics that you need to memorize. Just essentially memorize all of them. There are some trends that I'll talk about when it comes to oxygens. Typically, there's trends if you have less oxygens than normal or more oxygens than normal. And I'll get into that. All right, so just memorize these. There are some patterns, but some you just have to memorize. Okay, so I said that off of the periodic table, we can predict charges of basically a lot of the metals and non-metals. This only works for main group elements. So for example, if I said, what is the charge of an oxygen if it's an anion? You should be able to predict what? Oxygen as an anion is what? 2-, because it's group 6 minus 8 is -2. Those you can predict. Lithium is +1 because it's group 1A. Barium is 2+ because it's 2A. So those I like to call fixed charge ions. Those come from main group elements. What you're seeing here highlighted, these are variable charged elements. A lot of them are transition metals. Okay, so with these guys, see, I like variable charge metals because with the periodic table, the main groups, you predict the charge, but these ones, the name has to tell you what the charge is because you can't predict it. So for example, manganese, which is in the middle of the D block or the transition metals, it can have a charge. A manganese cation can be a +2, +3, +4, +5, +7, any one of those charges. So when we have a substance with a particular charge, you always want to communicate to the reader what that charge is. So how we do that with variable cation charges is use the stock system. Essentially, we use Roman numerals to tell the reader what the charge is. And that's why I like variable ones, because it just tells you what the charge is. All right, so within here, like iron 3, Roman numeral 3, what charge is that substance? Iron +3. See, isn't it great? The Roman numeral tells you the charge. All right, copper 1 is what? Copper +1. Copper 2 is copper 2+, right? Convention, typically you put the plus on like it's 3+, but if you do it the other way, no one's going to correct you. It's just like a very, very small detail here. All right, or we can go the other way. All right, so recognize that cobalt, tin, gold, all of those are transition metals. All right, so these substances will need the stock system when you write out its name. So cobalt 2+, you'll want to write as cobalt 2 in its name. This is tin 4. Okay, and then this is gold 3. So I like the stock system for transition metals because you don't have to think about it. I will point out some exceptions. All right, so here, silver, zinc, and aluminum right there are actually, they kind of fit within transition metals. You'd predict that they would be variable, but they're actually a fixed charge. So zinc as a cation is always +2, zinc 2+. So that means you don't use the stock system ever when naming a zinc compound. Same thing with silver. Silver as a cation is always +1. So you just say silver. You don't have to say silver 1. And then aluminum is always aluminum 3+. Yes?
Is there any time you'll have to denote it negatively with the transition metal?
No, because metals typically form cations, yeah. If you go into really, really higher level stuff, yes, but in this class, no. Metals form cations. All right, so yeah, these exceptions always are a fixed charge. They're always that charge, so you don't use the stock system. So no stock system. Okay, all right, let's get on to naming. Oh, no, not yet. So writing ionic compounds. So what do we do when we put together ions? We need to make sure when we form a ionic substance, an ionic compound, that it's charge neutral, essentially. So if we have differing charges of a cation and an anion, we need to make sure that the total charges cancel each other out. All right, so just working through these examples, if we have a magnesium 2+ and an iron- ion, and we combine those, what type of ratio of the atoms would we see in the compound itself? We would need how many, so I like to look at the charges. So magnesium's 2+, and then I ask myself, how many fluorines do I need? Yeah, I need 2 fluorines to balance that out. So how we write this, you always write the cation first, and then the anion. This is where we now use subscripts to tell the reader how many atoms are per molecule unit. So this would be MgF2, because we want 2 fluorines to counteract the +2 charge. All right, some people do the charges and they swap them, whatever works to help you get to a neutral molecule. Because if we just had 1 magnesium and 1 fluorine, then it would be overall +1 charge. We can't have that for a neutral compound. All right, so this one, barium and carbonate. So what's the ratio between the atoms? The ions that we need. 1 to 1. So how we write this, we just write barium and then 1 of the carbonates. All right. The next one, ammonium phosphate. So looking at the charges, we have a +1 and we have a -3. So we need 3 of the cations, right, in order to balance that out. So how we write this, If you need to write 3 of a polyatomic or like a multiple of a polyatomic, you put the whole polyatomic in parentheses. That looks really weird. And then around the parentheses, you put a subscript, so subscript 3. So I'm telling the reader, hey, take the whole ammonium, but I want 3 of them. And then phosphate. And because phosphate, I only have 1 of the polyatomic, we don't need a parentheses there. Okay, and that's why with barium carbonate, we didn't need parentheses there, because it's just 1 of that unit. All right, okay, so that's how you make ionic substances. Okay, so what does an ionic substance actually look like? So I lied to you a little bit in chapter 1, but it's fine, I'll fix it now. All right, so we said, if we look at these 2 substances, right, and I asked you, and I said, okay, those are pure substances, right? They both are compounds, right? Because sodium chloride, that's 2 elements together in 1 unit. Water, H2O, 2 elements in 1 unit. We said that those are compounds, right? Do you remember that, chapter 1? Okay, so compounds, we said compounds make molecules, right? Where we have more than 1 atom bonded together, molecules. So I lied a little bit. Only H2O is a molecule. NaCl is actually not a molecule. It has a better name for it, okay? So I will just kind of correct myself. Water is a molecule because covalent bonds form the substance. That's really the reasoning there. Covalent bonds form the substance, and we'll get into more detail there. NaCl is actually a formula unit, and I'll tell you why in this slide. But they're still compounds. They're still compounds. If you say, you know, a NaCl molecule, no one's going to correct you, essentially. But really, NaCl is the formula unit for salt. The reasoning is because salt looks like this. Those little balls are the alternating cation anions in a salt structure, right? If you took a grain of salt and you cut it in half, all right, and you have 2 grains of salt, the structures on the atomic level look exactly the same, right? Where we have these alternating cations and anions. Salt's still a pure substance. It's still a compound. It's just we can't call it a molecule because molecules are actually discrete. Like you could pick up 1 molecule of something. I can pick up 1 H2O molecule because covalent bonds hold it together. But you can't pick up one formula unit of NaCl. NaCl, that just tells you the ratio of cations and anions in this entire structure. That for every 1 sodium cation, you will see 1 chlorine anion. So saying molecule of NaCl technically is incorrect. We say formula unit because that expresses the simplest ratio within there. So here's two examples of different formula units of ionic substances. NaCl, we have those alternating balls, and here's magnesium oxide. So same type of deal. We have this extended network of cations and anions in this repeating structure. All right, so that's what ionic substances look like. So keep that in mind. That comes up a lot. All right, I have an exam question that looks like that. Okay, so now naming. Lots of just memorization here. All right, so I'll try to make it really clear where the strategy and categorization for how to name things. So first we're going to do ionic substances. All right, so the first thing is being able to recognize something is ionic. So when something is ionic, typically there's a metal and a nonmetal, or there's ions. So there's like a polyatomic ion or something. So that's like the first thing you should recognize. Basic rule for ionic compound naming: name the cation, then name the anion. Never, ever, ever, ever tell me how many of the cations and anions there are. Never. That's for molecular naming, right? So because the reasoning is we never tell the reader how many cations and anions are in the formula because we can always predict what the charges are, always. So if we know the charges, you know, as long as you understand, you know, canceling out positive and negative charges, you should be able to get to the correct ratio of atoms within there. So that's why we never, ever write in the name for an ionic substance how many ions are there. So for example, these different substances, this is going to be magnesium fluoride. So magnesium fluoride. It's not magnesium difluoride, it's just magnesium fluoride. Okay. This one is barium. So we name the cation, then the anion. Sulfide. Because we can always predict the charge of barium, we can always predict the charge of sulfur, and then combine them together, we should be able to get that ratio. And then finally this one, what would this be? Aluminum. I didn't teach you anion naming rules, that's on another slide, but oxygen is oxide. So it's aluminum oxide. It is not dialuminum trioxide. It is not. And I can bet you that if this question was on the exam, dialuminum trioxide would be an option, but that is not correct because we can always predict the charges of these things to get the proper ratio. So this is aluminum oxide. Okay. All right, so let's keep going. So more details. How do we name the cations? Cations are really nice when it's just one metal. If it's just like one element, the cation name is the element name. Yay. The exception, kind of, is if we have a main group element where you can predict the charge. If it's a fixed charge, then you just name the element. But if it's a variable charge element like tin, titanium, iron, cobalt, like any of those transition metals, you need to use the stock system in the name. All right, so let's go through this, going through these substances. I like to ask myself, okay, is this ion a main group or is it variable? Is it fixed or is it variable? Cesium, where is that? It's in group what? 1A, so that is a fixed charge. That cesium is always a group 1, like always a +1 charge, so we just call this cesium. But Fe3+, that's iron. Iron is a transition metal, all right, so typically variable, so we want to actually call this iron 3. Sodium is fixed, so we just call this sodium, like sodium ion or whatever. Calcium also fixed, so this will be calcium. Lithium is also fixed because it's a group 1A, lithium. But copper is a transition metal. This is a variable charge or transition metal, so we actually call this copper 2. Okay, so that's cations. And then the one polyatomic cation you need to know is ammonium. Same thing from that list, okay? All right, so let's keep going. Anions. So we'll do the simplest thing first, anions, when it's just one element, typically a nonmetal, right? If it's just one nonmetal element, we take the element name, we replace the ending with "ide." So oxygen, if it's O2-, we call that oxide anion. Or fluorine, but F- is fluoride. So ide, anions, you get that ide ending within there. Okay, and then you can, determine the charge. It's the same stuff as we did before. So if we look through these, okay, F-, this would be what anion name? Oh, I already said it, it's fluoride. Oh, and how you spell fluorine, I always forget, I'm a really bad speller. It's not flour. That's how I memorize, it's not flour. Because you'll try to write fluorine or fluoride, but it's not. So it's the U and then the O. That's how I memorize it. It's really bad, I know. Okay, sulfur. This is what anion? Sulfide. Okay, so the commonality between all of these is just one element. These are monoatomic anions. So hydrogen, hydride. N3-, nitride. Cool. All right, so that's how we name anions. So if you have just like a monoatomic metal and a monoatomic nonmetal for your cation anion, that's how you name it. So we can name all those now. All right, okay, so then things get complicated when there's polyatomics involved. Again, those anion polyatomics you just need to memorize. What I mean by polyatomic, typically we have more than one element covalently bonded together, and the overall thing has a charge. So ammonium, NH4, that has an overall plus charge, but there's multiple atoms in that whole kind of particle, and it all stays together within there. So typically with polyatomics, what you'll see is oxygens attached to some nonmetal. And so you see the names are similar within there. So like nitrogen, if there's oxygens attached to a nitrogen, we call that nitrate, nitrate anion, all right? So that's with some of these non-metal polyatomics, you just need to memorize what the base name and formula are. So like nitrate, sulfate, chlorate, phosphate. And then once you memorize those base polyatomics, once you start adding or removing oxygens, then it follows a trend. So if you, I think what's here, nitrate, if you add an oxygen, you add a per prefix plus an 8 suffix. So phosphate would become per phosphate, for example. If there's one less oxygen, you change the ending to "ite." If there's two less oxygens, you keep that "ite" ending and you add a hypo prefix. Typically, the charges don't change for these things. So for example, I told you to memorize nitrate, sulfate, and chlorate. Okay, so nitrate, if we remove an oxygen, that becomes what? Nitrite. So there is a trend. There is a trend. Sulfate, so what are we doing here? We're removing an oxygen, so what does that become? Sulfite. Sulfite. So note here that the charge doesn't change. All right, and then chlorate. This one's pretty tough. So this is like what I call my base polyatomic. Okay, so here's chlorate with 3 oxygens. So we added an oxygen. So what name does this become? Chlorate becomes perchlorate because we added an oxygen. So we note that we kept that 8 ending. We just added a per. And then if we go to ClO2, so again, relate this to your base name. So we removed an oxygen from chlorate. So this becomes what? Chlorite. And then the next one, we actually remove an additional oxygen. So this becomes hypochlorite. I forgot an H, but you know what I mean. All right, okay, so just practice those. Practice those. Okay, and now you can just put together your ionic substances. Now that you have your cation names, take note, do you use the stock system or not, or your anion names, all right? And is it a monoatomic or is it a polyatomic that you need to memorize? Okay, all right, so let's do an example here. All right, what if we combine 2 elements? All of these are main group elements. Okay, because that's the only way we can do this. So if we combine a calcium and a chlorine, you can predict the formula because based upon the location of calcium and the location of chlorine, you can predict the charges, figure out how to make a neutral substance, and then name it. So that's very, very comprehensive within there. So how I approach this one, oh, here you can see my strategy. All right, with all of these questions, because I just give you the name of 2 elements. I ask you, okay, what's the formula and name of your thing? So what I do is identify the metal cation, predict the charge based upon its placement. Then I identify the nonmetal anion, predict the minus charge based on its group number. Then combine it to make the neutral compound, and then name it. So that's my strategy for naming. So let's see, oxygen and lithium. So my first question is, what is the metal? Lithium. Lithium's the metal, so based upon its location, lithium is typically what charge? +1, because lithium is in 1A, so it's lithium +1. Oxygen is the anion. It's in group 6A, so it is a -2 charge. So I will say O2 minus. So I think to myself, okay, how can I combine those 2 things to make it charge neutral? It's going to be lithium, 2 of them, oxygen. All right, and then we name it. So I ask myself, oh, well, first I see, oh, it's ionic, so use ionic naming rules. Lithium is a fixed charge, so I just name it, and then I name the anion. So does anyone want to name this? Yeah. It's simply lithium oxide. Lithium oxide. Not dilithium oxide, just lithium oxide. Yes, I can. All right, so let's keep going. Aluminum combined with oxygen. So aluminum is the metal. It is typically a +3 charge. That's one of our kind of like exceptions in the transition metals. But you can also see aluminum is in group 3A, so it makes a 3+ cation. Oxygen, again, so it's O2 minus. So when we combine this, we get a substance. If we have 2 aluminums and 3 oxygens, we get that charge balanced. And so this would be aluminum oxide. Okay, fluorine combined with potassium. So fluorine is group 7A, it's an anion, F minus. Potassium is group 1A, so it's K plus, so it's just KF. So this is potassium, potassium fluoride. Okay, and then this last one here, yeah. Are there any, I don't have any polyatomics here. Yeah, so the question is, we're not doing any 8s or ites or pers or hypos because there's no polyatomics. These are just straight monoatomics that we can just predict their charge off of the elements off where they are in the periodic table. So that's why it's a little bit different here. A monoatomic, so if I'm talking about sulfide, S2 minus, that's monoatomic, just one element there. A polyatomic, so SO4, 2 minus, that's one that you have to memorize. See how there's multiple atoms there? Yeah, so within these questions, I don't say anything about sulfites or sulfates or nitrates. It's just the straight monoatomics. Okay, all right. So this last one, I just give you the charge of iron here, which is nice. So iron 3+ combined with oxygen, again, it's O2 minus, so this will be iron 2 of them with O3 of them. Okay, but within here, iron, it's one of our transition metals, so we have to use the stock system. I can't predict the charge. I can't predict the charge. They had to give me the charge. They had to give me the charge. So this is iron 3 oxide. That's rust, by the way. Like rust on your car. All right, so definitely practice these. There's tons of examples on those overview sheets. Here's my strategy. Okay. It's just like predict the charges, combine it. All right, so molecular compounds. We talked about ionic. So make a new box in your mind. We talked about ionic, metal, non-metal. That's in one box. This is a different box. Molecular compounds. These are only have non-metals in a formula, all right, when there's just non-metals. So there's something special that happens when there are just non-metal atoms in a compound. We form covalent bonds, and we form molecules of those substances. They're all those atoms are connected with covalent bonds. So there's special characteristics that you see within molecular compounds. Common molecular compounds we see are diatomic molecules. So these are, I guess, 7 diatomic molecules that you need to memorize, okay? So these elements actually exist as a molecule, all right? So 2 atoms bonded together in one molecule. Memorize them. So when I say nitrogen gas, I am referring to N2. That's what occurs naturally in our world. Versus when I say like a nitrogen atom or atomic nitrogen, then I am talking about just a nitrogen atom. Right? Or if I talk about liquid bromine. Liquid bromine, it's an element, but it is one of our diatomics. So when I say bromine, I mean Br2. But when I say argon gas, argon is not one of our 7 diatomics, so I am just talking about argon, Ar. So that is an atom, also an element, okay? So keep that in mind. Or if I say oxygen gas, like in combustion reactions, you burn something in oxygen. I'm not talking about O, the atom, I'm talking about O2, the molecule. Okay, so within molecules, we talk about molecular formulas. That's how we represent the number of atoms or the composition of a substance. Okay, all right, so molecular formulas just tell us the number of atoms in a molecule, just the composition. There are other types of formulas that we can express and use with other scientists to express what's going on in a substance. Structural formulas, they give us a lot more information about a substance. So here's hydrazine, so it's N2H4. Okay, all right, I know that there's 2 nitrogens, 4 hydrogens, but these structural drawings give me a much better picture of what's going, how those atoms are actually bonded to one another. And remember, the secret to chemistry, composition and structure is what dictates chemical reactivity and behaviors that we see. All right, so those are some formulas. This last one here is a little bit weird, and you might just hold on until we get to chapter 3 and 4. Empirical formulas. You might say, like, what's the point of these? So empirical formulas, it's like a molecular formula, but it's the simplest ratio of atoms. Okay, it's the simplest ratio. Empirical means by experiment, and I'll expand more on that next chapter. But so for example, hydrazine is N2H4. All of those subscripts are divisible by 2. So we can express an empirical formula, an even simpler way to represent the ratio of atoms as NH2, right? Because we can divide by a multiplier of 2. Right, so for a lot of compounds, we can relate molecular and empirical formula by some multiplier. All right, so we'll pick up back here on Wednesday. So you should be able to fill out this slide relating molecular and empirical formulas and identifying the multiplier.